Podcast 2, Conductivity, Permeability, and Why Eddy Current Loves Aluminum. Welcome back. In the first podcast, we talked about what eddy current testing actually is. We stripped away the mystery. We talked about coils, magnetic fields, induced currents, impedance, and why ET is an electrical current flow. Now we're going to tackle the topic that separates beginners from people who actually understand why ET behaves the way it does: conductivity, permeability, and why certain materials are easy while others are a giant pain in the ass. By the end of this lesson, I want you to understand why an inspector might use 200 kilohertz on one inspection and 6 megahertz on another. I want you to understand why aluminum is the sweetheart of the ET world. And I want you to understand why steel often makes ET technicians reach for aspirin. Tash, the two material properties that rule everything. If you've nothing else from this lesson, remember this. Most eddy current inspections are controlled by two material properties: electrical conductivity, drive almost everything; signal strength, depth of penetration, frequency selection, noise levels, probe choice, interpretation difficulty, everything. The inspector might think he's inspecting for cracks. Well, the instrument is actually responding to conductivity and permeability changes. The crack is just one way those properties get disturbed. Conductivity. First, let's start with conductivity. Conductivity is simply a material's ability to allow electrons. High conductivity M-Sili. Low conductivity means electrons encounter resistance. Think of a highway. High conductivity is an empty interstate through Montana. Low conductivity is downtown Houston at rush hour. Same number of cars. Very different movement. Why metals conduct electricity? Metals have electrons that are relatively free to move. That's why metals conduct electricity. Copper conducts very well. Silver conducts even better. Aluminum conducts well. Titanium doesn't conduct nearly as well. The reason comes down to atomic structure and how much resistance electrons encounter while moving through the material. Conductivity. A P would allow electrons to move with minimal interference. Unfortunately, engineering materials are not perfect. They contain alloying elements, grain boundaries, dislocations, residual stresses, precipitates, cold work, heat treatment effects. All of those things create obstacles for electron flow. This should sound familiar. You already know these things. Same things that influence mechanical properties often influence conductivity. Conductivity in welding engineering. This is where your welding background becomes useful. Think about precipitation hardening. Suppose we take 6061 and treat it, then we age it. What happens? Strength changes, hardness changes, microstructure changes, conductivity changes too. File site, turn file 1, turn file 0. The same metallurgical events that affect strength is one reason ET can sometimes be used to verify heat treatment condition. Now resistivity. Now let's talk about resistivity. Resistivity is simply the opposite of conductivity. High conductivity means low resistivity. Low conductivity means high resistivity. Y is how easily traffic moves. Think of resistivity as how much traffic congestion exists. They're describing the same situation from opposite directions. That scale. Sooner or later, you'll hear ET inspectors talking about percent IACS. What is that? IACS stands for International Annealed Copper Standard. Someone needed a reference. Copper became the reference. Pure annealed copper was assigned a conducti. Everything else, copper equals 100%. Other materials become percentages of copper. Simple. Why use percent IACS? Because it's convenient. Instead of talking about conductivity in complicated units, inspectors can simply compare materials against copper. Copper becomes the ruler. Everybody else gets measured against it. Typical conductivity examples. Let's build some intuition. Copper is roughly 100% IS. Aluminum alloys might be roughly 25 to 45% IACE. Titanium alloys may be around 1% IAC. Certain nickel alloys may be around 1 to 3% IACS. Think about that. Titanium may conduct electricity 30 times worse than aluminum. That becomes extremely important, and E behaves differently than titanium. Let's imagine the probe is producing a magnetic field. The field enters copper. Copper responds aggressively. Strong eddy currents are generated. Strong secondary fields develop. The primary field is opposed strongly. Penetration becomes shallow. Now let's switch to titanium. Titanium doesn't conduct well. The same magnetic field produces weaker eddy currents, weaker secondary fields, penetration. Same probe, same frequency, completely different behavior. The counterintuitive part. Most students initially think activity should mean deep sense, right? Electricity flows better, should go deeper. Actually, the opposite happens. High conductivity creates stronger eddy currents near the surface. Those strong eddy currents create strong opposing magnetic fields. Penetration becomes shallower. Low conductivity creates weaker eddy currents. Less activity creates weaker eddy currents. Less opposition, greater penetration. This is one of the most important concepts in ET. Why aluminum is ET heaven? Now we get to yes, ET love aluminum. Several reasons. First, aluminum conducts electricity well. Second, aluminum is non-ferromagnetic. Third, its behavior is predictable. Fourth, near the surface, exactly where ET performs best. Fifth, permeability isn't trying to sabotage you. All the inspector really has to deal with is conductivity and geometry. Life is good. Why Aerospace fell in love with ET? Think about the typical aircraft inspection: aluminum skin, fastener holes, lap joints, fatigue cracks, stress corrosion cracking, all near the surface, all highly conductive material, all non-ferromagnetic. That's basically a dream scenario for ET. File site, turn file 0 and turn file 1. Now let's talk about permeability. This is where things get ugly. Magnetic permeability describes how easily a material magnetic field formation. Non-ferrum tie values close to 1. Aluminum, copper, titanium, nickel alloys. Life is simple. Ferromagnetic materials are different. Steel, low alloy steel, many carbo-endless steels. Now permeability becomes a major factor. Why steel is ET hell? This is not because ET can't inspect steel, it can. The problem is interpretation. Steel introduces another variable, conductivity, plus permeability. Now the signal responds to both, and permeability is not always stable. Heat treatment changes it, stress changes it, cold work changes it, composition changes it. Now trying to determine whether a signal is a crack, a permeability change, a geometry change, or some combinate. Why permeability masks flaws? This is one of the biggest practical issues in ET. Suppose a crack creates a certain signal. Now suppose a permeability variation creates a similar signal amplitude. The instrument sees, the display shows both. The inspector has to separate them. This is where phase analysis becomes critical. And this is why advanced ET instruments spend so much effort analyzing phase angle. A practical example. Imagine you're inspecting a steel landing gear component. There is residual stress from our local hardness variations. There are permeability variations. Now a small crack appears. The crack signal may be buried inside all that other information. Finding the crack becomes much harder than finding the same crack in aluminum. Why frequency selection changes? Now we arrive at one of the important practical concepts. Frequency selection. Frequency controls penetration. Conductivity influences penetration. Permeability influences penetration. Therefore, frequency must be adjusted for different materials. Aluminum example. Suppose we inspect aluminum. Moderate conductivity, low permeability, a few hundred kilohertz may work beautifully. Good sensitivity, reasonable penetration, excellent signal QIM. Example, titanium has very low conductivity. If we use the same frequency as aluminum, penetration becomes much deeper, sometimes too deep. Signal response may become weak. Therefore, frequency often gets increased substantially. It's not uncommon to see frequencies in the megahertz range. Nickel alloy example. Nickel alloys also tend to have relatively low conductivity. Again, higher frequencies often become useful. The goal is maintaining sensitivity while controlling penetration depth. Steel excess permeability. High permeability dramatically reduces penetration depth. Therefore, frequency choices often become completely different. Sometimes lower frequencies help, sometimes filtering helps. Sometimes inspectors use techniques specifically designed to manage permeability effects. The answer becomes application dependent. The inspector's thought process. Experienced start by asking, what frequency should I use? He starts by asking, what material am I inspecting? What is its conductivity? What is its permeability? How deep is the flaw? What signal-to-noise ratio do I need? Then, frequency selection follows. The big picture: conductivity controls how strongly eddy currents form. Permeability controls how magnetic fields behave. Together they determine signal strength, penetration depth, frequency selection, inspection difficulty, interpretation difficulty, everything. Closing thoughts. Let's finish with 5 key takeaways. Number 1. Conductivity is the ability of electrons to move through a material. Number 2. Resistivity is simply the opposite of conductivity. Number 3. %IACS compares materials against pure copper. Number 4. Aluminum is ideal for ET because it is conductive and non-ferromagnetic. Number 5. Steel is more difficult because permeability variations can mask flaw indications. In the next lesson, we're going to tackle one of the most important topics in all of eddy current testing: frequency and depth of penetration. That is where the inspector begins to control what part of the material the test can actually see. And once you understand penetration, frequency selection suddenly becomes engineering instead of guesswork.